The topic that I'll be discussing today is convection and conduction. From syllabus, these are topics 2.3.1 and 2.3.2. So, to keep a building or a house at comfortable temperature in winter and in summer, if it is to be done economically and efficiently, it requires a knowledge of how heat travels. And it's not only about how you're building a house. It's basically heat transfer is a very important part of our lives, and it's present in every aspect of our life. If we count them, then let's just say when we're cooking stuff, when we're building houses, as it's mentioned over here, when we wear different clothes. Let's just say in winters we have different clothes, in summers we have different clothes. So heat transfer is a really important part of our life, and it's literally present everywhere you think about. Our the way we breathe, the way we walk, it's everywhere. And the air conditioning, the heaters, all of them work on these same principles. Now heat transfer is basically governed by some processes and some concepts, which are mainly three. And so heat transfer is basically done by conduction, COND, and then convection, and then radiation. That is the third one. So this is D. So basically, we have these three processes, and now we first thing that we are going to do is that we are going to, in this lecture, we are going to study these two, convection and conduction, and how they're similar, how they're different, and some of their different applications. So the handle of a metal spoon held in a hot drink soon gets warm. Heat passes along the spoon by conduction. Conduction is the flow of thermal energy, heat, through matter from places of higher temperature to places of lower temperature without movement of matter as a whole. So it's really fascinating if you think about it. How let's just say when you have this cup or this hot water in this glass, and you're just trying to you're stirring it, right? If it has, let's just say, coffee, and you're mixing the sugar. If the metal is made up of, let's say, if the spoon is made up of metal and it is a metal spoon, then after some time there's a high chance that you feel the warmth. You feel that although you're not touching, your finger is not touching the this is your finger, it's not touching the inside of the liquid itself, but still you can feel that your fingers are getting warm. Now, how does it happen? How does heat transfer from this point, or from inside of the liquid to the spoon itself? Now, the process how this happens is through basically conduction, and conduction is the flow of thermal energy through matter from places of high temperature to places of lower temperature. It's very important to know that in this case we are basically talking about mostly solids, that the concept in which the heat travels from a region of high temperature, which in this case is obviously I'm going to mark high temperature with red, and let's just take a highlighter out because it has a bigger, yeah. So this was the high temperature place, or this hole was high temperature place, because right, it is immersed in the liquid itself. So obviously it will be higher temperature than the part of the solid or the part of the spoon that was in the air and that was not immersed inside. So it basically travels upwards. The heat travels upwards to a region of from a region of high temperature to a region of lower temperature. So that's why heat travels like in this direction upwards, and then you can feel that heat, in over here when you're touching the tip of the spoon. So this is basically from here to where this is the definition of conduction that can be used and that should be written when asked in exams, etc. Okay. Now, the syllabus asks us to talk about some of the experiments that demonstrate the properties of different materials as how they conduct and their different conductivities. So this is basically the figure. We are going to first talk about the figure itself. So what is happening over here is that we have a tripod stand. So tripod stand is basically a stand which is like this, And now, if this is the view that I am drawing is a sideways view, and over on this tripod, we have these four metal, these four rods. First one is made up of brass, second one is made up of aluminum, then iron, and then copper. Now we're basically testing, or we're experimenting. The thing that we're talking about is basically the conductivities of how good these materials, let it be copper, iron, brass, aluminum, or steel, whatever we have in our setup, how good of a conductor they are. Now, I'm gonna first go through this description, and then I'm going to explain the diagram and how it's going to work and how it's gonna give us the results. So, um, a simple demonstration of the different conducting powers of various metals is shown in figure. A match is fixed to one end of each rod using a little metal melted wax. The other ends of the rods are heated by a burner. When the temperature of the far ends reach the melting point of the wax, the match is dropped. The match on copper falls first, showing it is the best conductor, followed by aluminum, brass, and then iron. So what happens is that, this point, the ends of the rods, they are in direct contact with the flame or the burner or the heat source itself. However, the point where we are basically studying, the area of our concern is this point where the paraffin wax is attached. Now, how is heat going to propagate from this point to this point? Well, the answer is simple. The thing that we're basically measuring, conduction. Heat is going to propagate from this point to the end of the rod by conduction, and the faster it propagates, or the faster it gets to the end of the end of the rod where the paraffin wax is being, is stuck to it, it's going to tell us that it's a better conductor. So the results show that copper rod, the matchstick that was attached to the copper rod using paraffin wax, drops first, which means that paraffin wax at the end of the copper rod melts first, which basically means that paraffin wax that was on this copper rod got the heat that it needed to change its state from solid to liquid first, which again tells us that copper is the best conductor among these four options. Then they're basically given this whole result that it follows by aluminum, brass, and then iron. So the best conductor is copper, then we have aluminum for the second, and then we have brass, and in the end we have iron. So this basically tells us the thermal conductivity or the heat conductivity. It is also very important to note that we're not talking about electrical conductivity. We are basically talking about how well does this material help in transferring heat. So it's called thermal conductivity or heat conductivity. Now this is another experiment that we are going to see of how it conducts, heat. So heat is conducted faster through a rod if it has a larger cross-section area, is short, and has larger temperature difference between its end. So the conduction basically depends on the area, the surface area, the cross-section area, and the length, and the temperature difference, which is the delta T. So it is directly proportional to the area, it is inversely proportional to the length, and then it is directly proportional to the temperature difference or the temperature gradient, we call it. In this experiment, I'm going to explain in next slide what we're basically doing. Before that, it's important to know that most metals are good conductors of heat. Materials such as wood, glass, cork, plastics, fabrics, they are not good conductors, and rather we don't call them conductors at all. We call them insulators. So we call them insulators. Okay, so yeah. Okay, So these are insulators, and metals are basically good conductors, out of which we've seen that copper is one of the best conductors, thermal conductor, heat conductors. So how do we perform an experiment to basically find out that metals are better conductors and wood is not the best conductor, or woods and glass and quartz, they aren't the best conductor? Well, basically, this experiment over here, it's not really written because it's a very simple experiment and it's not that complicated. So what's happening over here is that yeah. So this is a heat source, and these are two rods. One is made up of brass and the other one is made up of wood. Now they're attached with this white gummed paper, and when we apply heat to it, the gummed paper on this side exactly, on the wood side, it burns and it catches fire. However, the brass side, it doesn't. The reason is that when heat is applied to it, the brass rod, it immediately propagates the heat, through its length. The heat travels in this direction. But since wood doesn't have that property, the heat or the temperature, it just rises and rises and accumulates at this very specific point, and then the paper burns. And we see that happening in front of us. So that basically tells us how wood does not propagate heat through it. It does not transfer heat through it, which tells us basically that wood is not a good conductor. Rather, it is an insulator, that it does not propagate heat through its, microstructure at all. However, brass does, and brass does because it is a metal. So this basically justifies or holds to our hypothesis that we had first written. So this is basically an experiment that refers to it. Okay, now this is another experiment. Initially we're basically talking about all the solid examples, but what about liquids and gases? We have to conduct experiments that talk about the conductivity of liquids as well as um, solids and gases. So liquids and gases are also conductors of heat, but they conduct very slowly. Water is a very poor conductor of electricity, as shown in this figure. The water at the top of the tube can be boiled before the ice at the bottom melts. So what's happening over here is that yeah. So this is the whole instrument or the apparatus that is required in this experiment is very simple. It's literally a block of ice and then this metal gauze piece, and then we have water filled over it. Now what's happening is that if water was a good conductor and we provide it with some heat, this is the point where we are applying heat. This exact point is where we're applying heat. It should propagate to the side where there is less heat, which is this side of the test tube, where the ice is, that is lower temperature. But since it's a very bad conductor of heat, the heat propagates through this test tube really, really slow. And although you're heating this test tube directly, like it's directly above the fire, but the ice over here, it doesn't melt at all. That is because the water over here, it turns into steam itself. Like it rather turns into steam than propagates the energy towards the lower temperature side. It has two options. It can either transfer that heat to the other side, or it can just, the temperature can rise and rise and rise until it gets to the boiling point, and then the water turns into steam. So the conduction is so bad that very minimal melting happens, because very minimal conduction takes place. Hence, we can observe the boiling, but no melting or decrease in the size of this ice. Okay, conduction and the kinetic theory. Now we're going to talk about how conduction basically happens and how it's related to the kinetic theory that we have already studied or talked about. So, two processes occur in metals. Metals have a large number of free electrons which wander about inside them. When one part of the metal is heated, the electrons move faster and further. As a result, they jostle atoms in cooler parts, so pass on their energy and raising their temperature on these parts. This process occurs quickly. However, the second process it is much slower. Now, what is the second process? The atoms themselves at the hot plate make colder neighboring atoms vibrate more vigorously. This is less important in metals, but it is only where conduction occurs in nonmetals since they do not have free electrons. Hence, nonmetals are poor conductors of heat. Okay, now we have two things. Number one is free electrons, and the other one is the basically atoms or the molecules itself. The conduction that happens by the molecules itself, it's not as significant because that happens in metals and every solid ever. But the thing that makes metals stand out more is free electrons because they move faster and they basically wander inside all the structure. When one of the metal is heated, the electrons there move faster, their kinetic energy increases, and then they jostle around in the cooler parts, and hence that's how they propagate the heat energy. However, in the other case where we're talking about just atoms itself, the whole process of atoms transferring heat or kinetic energy is not that efficient, and it does takes place on a slower rate. So this entirely makes how metals are better conductors than the Now we've discussed the concept of conduction. Now we're going to move forward towards what convection is. Convection is, another process in which the heat transfers. Now, how is that different than convection? So convection is the flow of heat through a fluid from places of higher temperature to places of lower temperature by movement of fluid itself. Now, it's really important to know that the one of the most important points in conduction that we discussed was that there is no involvement of the medium or the material itself. However, over here, the concept is same that heat is moving from a region of higher temperature to a region of lower temperature. So the gradient is same from a region of higher temperature to a region of lower temperature to a region of lower temperature, and heat is moving, in this direction. It is moving like this. The concept is same. But the thing is that in convection, we're talking about fluids, number one, and we're talking about the movement of fluid, that the fluid moves itself. Streams of warm moving fluids are called convection currents. So, warm moving fluids, they're called convection currents. They arise when a fluid is heated because it expands, becomes less dense, and is forced upwards by surrounding cooler, denser fluid, which moves under it, which say hot water rises or hot air rises. Since we're talking about fluids, we include or we talk about both liquids and gases. Now, this phenomenon is really simple and it's really common in our daily lives. And when we install a heater, we put it on the ground. We don't install it, above or on the or like ACs. However, when we're talking about air conditioners, they are at some height. So because we put our heaters on the ground because we want the hot air to rise, to be near us. However, in air conditioners, we want the cold air to be basically the result. I'm going to talk about this more comprehensively after that, so it's going to basically make sense. So, warm fluid behaves like a cork released underwater. Less dense, it bobs up. Lava lamps, they also use this principle. So, basically, what happens is that, let's just say if this is a room, we have some air, and let's just say we have this conditioner that is installed over here, right? Now it is cooling some air. Now, as it is cooling some air, the air particles they get closer to each other, hence they get more dense, they get more heavier. Although, we're talking about basically density, but let's just say, just to imagine it or make it more convenient, let's think that they get more heavier. Like, so they they're denser, they move downwards. However, the hot air that was, on the bottom side of the room or the lower side of the room, which needs to be cool, it basically rises the hot air because the particles are not close to each other and they are all over the place and they are occupying more volume, so it's not as dense, so it basically rises just like in the water. So the whole concept that hot air rises, cold air sits, that's how our heaters work, that's how the fluid in the saucepans or whenever we're cooking it heats up, and that's how the air conditioners work. So we're going to talk about it now. Even in these lava lamps, that's basically how it's happening, that we have oil and we have different colors and then different mediums, and then we're heating it up, and we can see the convection currents, or we can see the whole movement happening because because um, they're colored and they're pigmented. So these are convection currents, but we can see them. So that they're really pretty. Okay. Now, convection in air black marks often appear on the walls or ceiling above a lamp or a radiator. They're caused by dust being carried upwards in air. Okay, when you're like in a room where there's it's a bit dusty and sunlight is falling on it, you can see that there are some air particles that often appear on the ceiling or above the lamp or the radiator. That's because the dust that is being carried upwards through the air convection currents, we can see that the hot air is rising. So at lab, demonstration of convection current in air can be given using the apparatus, which will be shown in the next slide. The direction of the convection currents created by a candle is made more visible by smoke or from a touch paper made by soaking brown paper in strong potassium nitrate and then drying it. Convection currents set up by electric gas or oil heaters help to warm our homes. They are also called radiators, and but they're really just convector heaters. They're called radiators, but you're really using convection as the main medium. So what's basically happening over here is that here we have this lighter lighted touch paper, which is just giving out some smoke, right? Now, although we are just like the smoke is coming from this direction, it should just stay here or accumulate. But because of the property that hot air rises, because this lighted candle, it has this layers, or it has this atmosphere of hot air around it, and that hot air carries this smoke that is caused by this lighted touch paper, and hence why we can see this smoke rise up. Because if there was no medium, or if there was no currents, or there was no let's just say um, mechanism to bring the smoke up, we wouldn't be able to see the smoke. We could just say see the smoke over here or settle over here. But the reason why we see it coming out of here is because of the hot air currents that are rising up. So this is basically demonstrating convection, that hot air rises, cold air sits. And that's about it. We have to discuss the demonstrations and um, basic concepts of conduction and convection. In the next one, we'll be talking about radiation, and then some applications of these heat transfers in our daily life.